Welcome again, my friends and followers. Let us talk about condensation, heat transfer coefficient. How can we estimate the condensation heat transfer coefficient of fluids as they pass through the tubes? It is meant here to talk and present the condensation process when we have internal flow in the tubes. Let us go to some details of this subject. Welcome, my friends and colleagues and followers. The condensation process is one of the important topics present in modern industrial applications in the field of energy and heat transfer. We may find the condensation process in many topics and fields of industry, such as petrochemical factories, refineries, food industry, power plants, air conditioning and refrigeration, and many other topics that is experienced in the field of thermal engineering. The prediction of condensation process and the performance of a heat exchanger is mainly based on the heat transfer coefficient and how accurate it has been predicted. Condensation can occur in different orientations: vertical, horizontal, single, or tube bundle. And in the present episode and the film episodes and videos, I will introduce the condensation process in different categories, whether it was external or internal flow. Thank you for your support and continuous assistance that is afforded by your side to the channel, and let us go directly to the objectives of the present episode. The main objectives of the present episode can be divided in first part related to the concept of internal flow condensation in horizontal tubes, and then we will pass through the methods and correlations that are available in the open literature to predict the condensation heat transfer coefficient, and then we will um, arrive at the closure of the present video. The concept of condensation in horizontal tubes can be described by the illustration as shown in this figure, that we have an industrial site where a condensation process is involved in these uh, layout and units of the process in the industrial side. Let us consider the horizontal heat exchanger as shown in this illustration. That is a shell and tube heat exchanger where the vapor flows following the red arrow through the tubes, horizontal tubes, and the final part of it to be condensate that is returned to the unit where it has been discharged to complete the closed circuit for that fluid. This is a simple illustration where the heat can be transferred from the condensate to a cooling medium, such as cooling tower water. And this is how the condensation process can occur or applied in industry. The flow regimes in the condensation process when the fluid passes through a horizontal tube can be shown in this illustration where the vapor enters. It could be superheated vapor where its temperature is higher than the saturation temperature corresponding to the operating pressure with the quality X equal to 1, that is vapor 100%. And as it passes in the tube, some heat can be transferred to the cooling medium, then a thin liquid of this condensate can cover the inner side of the tube and forming annular flow. And as the saturation temperature is approached, of course, that the condensation process will continue until we get X equal to 0, where subcooling uh, region can commence. In fact, the shape of the condensate inside the horizontal tube can be shown in this figure, that the condensation process inside the horizontal tubes is shear controlled or a gravity controlled mechanism. The annular flow pattern is usually associated with high vapor shear, whereas stratified flow appear when gravity is the dominant force. The condensation flow inside the horizontal tube is described in these figures, that for fully um, developed annular flow pattern, there is a thin uniform condensate layer, as we have mentioned that, and the entire tube wall in the condensation zone that is covered by this layer. Therefore, the heat transfer is controlled by vapor shear and turbulence. In the case of a condensation stratified flow, as shown in part B of this figure, that is the stratified, uh, a certain thickness of the condensate layer is built at the bottom of the tube due to the gravitational force, and a thin liquid layer adjacent to the wall at the upper part as shown in this illustration. Of course, in vertical tube condensation, the downflow inside the vertical configuration provides higher heat transfer coefficient, and the flow distribution is well predicted. This is just simple and brief for the condensation process that occurs inside the horizontal tube. It starts from annular, then we have stratified, and the The final part is called slug flow, where just a little part of the vapor is existed in the bulk flow of that fluid. The available correlations, of course, there are numerous number of these correlations are available in the open literature, but I will mention some of them, and you may find more in the list of references which are seated at the bottom of this video in the description box. So I will start with Nusselt equation in 1916, which was based on a condensation process on a vertical cooled plate, as shown in equation 1a. And here we have the uh, uh, condensate loading defined as m dot divided by L tube. And this equation can give a heat transfer coefficient of the condensation process inside horizontal tube. And we will find that this correlation is a quite conservative one. Uh, of course, this is valid for stratified flow model in a horizontal view. We have Eckers et al. In 1959. He presented the equation similar to the general form of convection heat transfer coefficient. And here we have the constant C and N depends of R equivalent, and R equivalent is defined by G equivalent as shown in this equation, in equation 3b. And these values, I mean the numeric values of C and N depends on R equivalent, Reynolds equivalent, and for Reynolds equivalent greater than 5 times 10 to power 4, they give C equal 0.0265 and N 0.8. And for Reynolds number equivalent less than 5 times 10 to power 4, they also sheeted these two values for these parameters. We have Chateau in 1962. He also presented a general form for condensation heat transfer coefficient as shown in equation 4a, where I sub fg represents value that is corrected latent heat of the fluid to include the sensible part, the second term of equation 4b, and he used Reynolds vapor as the total mass velocity, and it is applied for gravity-driven film condensation in horizontal tubes, and the properties of all the calculation of the thermal properties of the fluid, uh, all of these except I sub Fg and rho V are calculated at the saturation temperature. And of course, we have to mention that the other properties are calculated at the film temperature except these two. And we have the vapor Reynolds number is evaluated at the inlet vapor quality conditions. For example, if it was saturated vapor, then X equal to 1. And it may enter as a mixture, X equal to 0.9, 0.8, or something like that. Then we have to use these values in the prediction of all of these um, parameters. But here we have the inlet vapor quality should be mentioned in these equations. Uh, what we have also, we have Tang in 1997. He presented a form of equation similar to the equation as presented by Ecker hackers and others, but with including the effect parameter f sub p, and f sub p is defined as shown in equation 5b. These are the general forms of these equations and where can be used. Of course, we have to mention that this equation is only applied for horizontal tubes. And finally, I will mention equation by Bodal and others in 2012. It is presented in the form that the heat transfer coefficient is they included the effect of P sub R, which refers to the reduced pressure, and the quality of vapor in the form of equation 6. And this equation was applied for obtained for refrigerant R134A, R404A, and R407C, which is mixture that is zeotrope with little temperature glade between the dew and the saturation temperature. Of course, this equation is valid for the conditions where its diameter is quite small, between 0.31 to 3.3, and the saturation temperature between 20 to 50 Celsius with the G value as shown in these figures. And the accuracy range was between plus minus 25% for the data which were obtained from their experiments. Of course, we have to mention here when you are going to use these equations in the design, you have to calculate the annular heat transfer coefficient, annular, where it occurred in a flow which shear control condensation, and stratified flow, where it is controlled by the gravity uh, part. Then we should choose the higher value in calculating the overall heat transfer coefficient, which produces the surface area of that heat exchanger. Dear friends and colleagues, followers of thermal engineering concept and principle channel, we arrived to the final part of the present video, which represents the closure. And we introduced the concept of condensation in horizontal tubes and its regimes. And then we passed through some of the available correlations to estimate the heat transfer coefficient of condensation in horizontal tubes. And you may find a list of valuable resources, in fact, for some references which can be passed through, and you may find one of my books as well that is related to this topic, The Principle and the Practice of Heat Transfer. And if you have found the content of the present video is useful and for you and others, please subscribe and share what we have with others to achieve the goals of from creation of this channel. And then I will see you in the next part of the condensation process in horizontal tubes. Bye bye.